Good afternoon, everyone. My name is Jake Wharton. I'm here to talk to you about how you can talk to your terminal and how it can talk back. So terminals are having a bit of a resurgence lately, for better or for worse. They never really went anywhere. It's really one of the oldest computing technologies we have. They're 50 plus years old. And like text-based computing interaction through text-based stuff is sort of one of the foundational things of our industry, similar to how the web is foundational. Everything can run a browser. Everything usually has some way to connect a terminal to it and talk. This thing is actually not a terminal. This is a shell. A shell is a program that runs inside your terminal, and it's responsible for interpreting your commands and launching other programs. The thing around it is the terminal, and that's what we're going to be talking about today. And technically, that thing is also not a terminal. It's a terminal emulator. This is a terminal. These don't exist anymore for all intents and purposes, but while it looks a lot like a computer, it is a keyboard, it is a screen, and it is just enough computing to be able to connect to a remote system, probably the size of a room in the next room over. But those don't really exist anymore. What we know nowadays as a terminal is sort of the thing, the terminal emulator that you run. And nobody's going to fault you for calling this a terminal. That's totally fine. OK, so we're going to be spending a lot of time in the IDE today doing some live coding. Yep. And we're going to start from the most primitive of primitives, which is how do we even get things onto the terminal? The literal hello world. And so I have this application here. It's just a bog standard Kotlin native running on building for my Mac. And all I have is print hello world. And so I'm going to build this. Oops, I meant to turn off suggestions so you don't see. So I'm going to do link, debug, executable, Mac ARM. And we'll cheat here and do talking to terminals. And I should get hello world. OK, so what we've just done is sent a series of bytes to our terminal, and it has interpreted them and rendered them on screen. This seems like a thing that we take for granted, but it's like a really foundational sort of primitive on which tons of cool things can be built. And it's not a unidirectional messaging thing. It's bidirectional. And so what I can actually do here is also take input. And so in addition to outputting code, I can type hello. The terminal is interpreting my key presses, sending that as bytes over to my program. My program's reading them, spitting them back out, and they're getting rendered. OK. So these are the standard streams that every process that's launched is afforded. And so our process was essentially handed these from the person who created it, which in our case was the shell that I'm running. It's responsible for setting up where they point. And usually, by default, it's going to be pointing towards that terminal. And so the things that I write to standard out or to standard error will be displayed in the terminal, and the things that I type on my keyboard into the terminal will get routed through into standard in. Every process has these, and there's ways that the reason we use a shell is because it can manipulate these. And so if you've ever done a to arrow to dev null to hide the errors, what you're essentially doing is unhooking standard error from the terminal and pointing it at dev null. Or if you've redirected a program's output to a file to use somewhere else, you're unhooking standard out and hooking it up instead to a file. We'll talk a little bit more about redirection later, but I want to go back to programming things. OK, so what we've done here is render printable characters. Everything we send gets put on the screen. Everything I type gets sent back to the program. But there are other ways that we can communicate through this channel to the terminal. And these things are called ANSI escape codes, which is where we start. This is very big. So we're going to start here. Old terminals were basically ASCII, and so all these primitives are built upon text. And so some of the special characters that we take for granted, if you think about what a new line is doing, it's telling the terminal to move everything up and to create a new line down below. And there's other instances here, and what we're going to look at is this one at the very bottom, the escape character. And it shows you what it's the hex is 1B, which is what we're going to use. This is how you would like reference it in different things. And it starts all of these escape sequences. There are multiple escape sequences. We're mostly going to focus on one of them, which is this control sequence. We're going to try and control how the terminal is outputting stuff. Oh, it even says it's the most useful. Yes, it is the most useful. We might, if I remember to point them out, I will also try and point out that we will see some DCS and OSC ones. But they're much less used. CSI is sort of the primitive that most things are built upon. So I will skip down to that. The way CSI works is you send those bytes, the escape character, and then I forgot to point out, but it starts with this open square bracket, and then it's sort of like a conditional. You can do a bunch of things with it, and the switch that it uses to determine what it's going to do is actually the final byte in the sequence. So if I scroll down here to a table that shows some of the codes, we can see that there's like cursor manipulation, which we'll get to in a second. But if you look, like it starts with CSI, which is the escape, and then the square bracket, a number, and then A, and then down is B, forward is C. And so it's the last character that's controlling the behavior. And there's a bunch of these. I'm going to scroll down here. The one I want to get to is graphics. We're going to change how our text looks on screen. So this is a CSI. It takes a number, and it specifically ends in the character lowercase m. And if we don't give a number, it's treated as a reset. And so this has some stuff that we're used to in like text presentation, bold, italics, underline. And so let's make I gotta make sure I'm following my notes here. Let's make our text bold. So 1B was the hex for escape, square bracket, and then bold was 1. And I'm actually going to pull this out because I will be using it over and over again. And now when I render, it's subtle, but it's there bold. I can do this to make it, we'll do all the things. 3 and 4, so that was italic and underlined. So world is now italic, bold, and underlined. And I can do like just CSIM, which has no number, so that's the reset. So our exclamation point should go back to being the normal rendering. In addition to the, I don't know what you call these, sort of like weights, we can scroll down here and get to colors. So the range 30 to 37 or 40 to 47, there's actually more ranges than that. We'll click over here and we'll see a nice pretty table. So if I want to make, let's go with red here, and we'll make world red. What was red? 41? 31. Now I get red. And just because we're doing color doesn't mean, so there's foreground colors, there's also background colors. So like, this second column is background colors. This says white, but it's actually like dim white, which we know as gray. If you want actual white, you have to do bright white. So we can put a background color with 47, re-render, I get a background color. And I can also I can put, underlines back as well. Okay. Let's go back to, so that's presentation in terms of like manipulating the characters that we're already sending. Now I want to go back to the thing we first saw in CSI, which was the cursor movement. And what this is going to allow us to do is move our cursor around the screen in order to change where stuff renders. How can I get back to that? I'll just scroll up, just so we can see. Okay, so what we're going to do is we're going to move the cursor forward. So I'm going to write hello, and then I'm going to move it over a little bit so that the world is spaced further away. So we'll do CSI 5C. And what this should do, so we write hello, we write the space was still there, and then we add 5, we move the cursor. We're not writing like you could write 5 more spaces, but we're actually just moving the cursor over 5 and then writing the rest of the line. And so we could switch this to D, which was cursor in the other direction, and look what happens. So what's happening here is we've written hello, comma, space. And then the cursor is moving back 5 positions, we'll call them, cells, and then we're writing the new strings over this. And so it's, you just see the final result here. What we can do is something like this. We'll break this up so that it's 3 distinct calls. So this won't change the program behavior at all, which I will show you. But if I add some nice sleeps, and rerun, you see the cursor, and ready? It jumps back 5, and then we overwrite it with the new characters. Now, when I looked at something like that the first time, it was like a little bit of a light bulb moment where this is not, this is very, very far away from seeing when you update like Docker or you run a Gradle build or a homebrew install or any of these other really sort of semi-rich terminal interactions. But this is the most primitive version of that mechanism. You write some characters to the screen, you wait until something else happens, move the cursor to a position that you want to update, and then you write more characters. And so we could just, we could get to the point where we put this in a loop or whatever and start creating these really rich interactive things. 95% of all the cool terminal shit you've ever seen is just these 3 very simple tricks used in an extremely effective manner. Okay, so I want to show now what happens when I redirect this to a file. Oh, I should have taken the sleeps out, huh? That was in my notes. Take out the sleeps before you do this. Okay, we're gonna. This is the hex output of the file, and the reason I'm doing this is because if I just cat the file, it looks exactly the same. But if you look at the actual contents of the file, the bytes that are changing the visual representation are still there. So this 1B, you'll remember, is our escape, and then 5B is the square bracket, if you would look it up. And then we have, I don't even remember what was next. Is that 54? No. Oh, that's the cursor movement. Yeah, so there's a trick here, which is you subtract 30, and that gives you the decimal. So 35 minus 30 is 5. That's our 5 position movement. And then I can't do this with ASCII, but I'm pretty sure it starts at 41. So or it starts at 40? I don't know, but that's the D. So that's our 5D, and then here's the color sequence, and then down here's hello world, here's our reset, and then here's our exclamation point, and a new line. This is uncommon. If you redirect tools to files, they won't do this. So if I just list what's in this directory, I get tabs, I get colors, I get this sort of visual treatment. If I redirect this to a file and then show it, none of that stuff is here. I don't have the tabs. I don't have the tabular structure anymore. All I have, it's kind of hard to see, but you can look over here and sort of see what's going on. But you can see the build folder and then 0.a, which is a new line. And then I have my build.gradle. And then I have the Gradle folder. I have my Gradle wrapper. I got some stuff that we're going to use later. There's the output file. It's just the contents of ls, new line separated. Or sorry, just the contents of the directory, new line separated. So it is somehow determining that it's not rendering to a file, and it's altering its behavior. Oh, I was supposed to connect to the conference Wi-Fi too before this. So I want to show you something with curl here. Whoop. We'll do it live. Do we agree? We agree. Okay, I'm going to curl this site. And what the site is going to do is send me bytes slowly. And so it's over a period, I don't even remember how long, 10 seconds. This is actually a lot slower than it was originally. We'll just do 10. Oh, that's still 100. So it's sending me these bytes over a couple seconds. And curl, the -n flag is basically telling it, don't buffer these, like output them as soon as you get the bytes. Now watch what happens when I redirect this to a file. Any guesses? Have you seen this before? It's writing those bytes to the file. My terminal's a little too small here. Let's make this a little wider so it's not as ugly. It's writing those bytes to the file as they get downloaded, while simultaneously, somehow, also producing output to the terminal. So if I look at that file now, I get my 10 stars. And you might think that like maybe it's doing special trickery or whatever to somehow include the sequences, but like no, the hex of that file is just the stars. So despite us redirecting curl to a file, it's somehow like going around our standard mechanism of providing, this inversion of control pattern where like the process doesn't know that it's redirecting to a file, except somehow it does. And like, how is it doing this? And while the answer is it's literally just going around the standard thing and looking up the TTY device. This is a standard thing where you can always just go and sort of grab the enclosing terminal, assuming that there is one. And so let's see if we can do that to ourselves. Okay, I was supposed to remove the sleeps. So we want to basically say hi to the terminal. I'm going to get rid of the cursor movement. We'll collapse this back together. I think that's where I'm supposed to be. So what happens when I print? Does anyone know how that even gets to standard out? If we follow it through, we get into an external function, so a function defined outside of Kotlin. You can see its name here. And I have that open. So this is C++, the Conan sort of standard, the standard library implementation for native. It's going to convert our stuff to UTF-8 bytes, and then it's going to call this other function to write it to the console. Whoop, that's fine, we're done with that. That's this function. We're not on Android, so that's for the Android native targets, not like when you're compiling normally to Android. And so we're going to end up in this branch, and we're writing to this standard out file number, which is it's a file descriptor. The numbers are actually standardized, and we're just sending the bytes to it. So the first thing we're going to do is we're just going to get rid of our print, and we're going to do that ourselves. So this is going to be my message. The first thing it was doing code to byte array. That's our bytes. And then because this is native, we have to pin the memory so that it doesn't move while we call into a function that's not Kotlin. We don't want the garbage collector to move where the bytes live. And we're just going to call write. We're going to do standard out. We're going to do the address of the first byte in our byte array. That's basically just the pointer to the first byte, and the number of bytes that we're going to write is however many we have. And that is an unsigned number. I will turn these off. They're kind of loud. And so this should be exactly the same as it was before. That one. And it looks exactly the same. We're doing the same exact thing print was doing, but we're now bypassing it. So now that we're doing this ourselves, now that we're talking to the terminal, sort of, or at least the standard out more directly, let's see if we can identify whether or not we're talking to the terminal. So I'm going to need this more than once. So I'm going to make a function and to call it. I want this to be first. Yes. And then this is what we're writing to right now. And so there's a built-in function. Let's change what we're printing to be terminal. We'll call this our subject. Oop, I didn't want a function. I wanted a variable. This is our subject. So we'll print the same thing no matter what, but we're going to determine whether or not the thing we're calling is the terminal, and there just happens to be a function called isATTY. What a mouthful. And so what this is going to do is allow us to vary our subject. So if we're a TTY, which means we're the terminal, we're going to say terminal. Otherwise, we'll say world. So that's that. We'll get rid of the braces. And I forgot my equal sign. OK. So now when I run, it says hello terminal, because we know we're talking to a terminal. If I redirect to a file, and I cat the file, I get world. And I can also replicate that by just skipping that and going directly to cat. So the standard out is the shell is hooking the standard out of my exe into the standard in of cat. And so when I do the isATTY check, it's returning false. And so now we can correctly identify whether or not we're talking to the terminal or we're talking to something else. We don't necessarily know. I mean, we can query other things about it, whether it's a file or a pipe or whatever, but in general, we don't really care. OK, so I want to go back and now replicate what we had earlier, which was the input. I want to be able to read from standard in. So I'm going to do this 1 byte at a time. We're just going to read a byte and print out a byte. So I got a pin again. What we're going to do is we're going to read from standard in. We'll read into our our byte array. We're just going to read 1 character. Also, I forgot to say at the beginning that I tried to not hand wave too much stuff away, but there is a little bit of hand waving just to save time. So like these read and write functions actually return the number of characters that have been written. And so if there's like buffers that are getting full, you actually might not be able to write the whole, like down here, you might not be able to write the whole thing. You'd have to do like a loop and whatever. We're skipping all that for the talk. So if you're doing any of this stuff, make sure. And how about this tie-in with Kotlin's new unused return value checker in 2.4 that you should turn on. That will get surfaced automatically, hopefully, because it's actually returning a value that you should not be ignoring. But we are going to ignore it. OK, so I'm reading and writing, and I'm going to add a thing here that will become a little more relevant in the future. But basically, if we get an input character, we're just going to use the letter C, C for quit. We're going to break. Sorry, I was supposed to be doing this in a loop. That's why it's not able to break. OK, why don't you like it? Still writing to cat. All right, so now I get my terminal output. I can type hello, and I get hello back. Does that look weird to anyone? Does that set off anyone's things? I typed hello, and nothing happened. I pressed enter, and then I got a second hello. Why, if we're reading byte by byte, why isn't every character I press immediately duplicated? And here's another fun one. I added in that check for when you type a C. I can type a C, and then I can backspace and type something else, and then a C. And it will quit. It will echo it back out, and then read it. And that's because the terminal is trying to be helpful to us. And technically, it's the shell also is trying to be helpful to us. And that's because it's in this certain mode. And the modes are called cooked or raw. And in cooked mode, which is the default, data is pre-processed before being given to the program. And so I'm like interactively able to write things, and then only when I press enter does it get sent. And then raw mode is what actually puts it in like when you open an editor or something in IDE, like Vim or Emacs or Nano or whatever, and you're typing sort of in real time. So let's see if we can put, now that we know that's why we're getting this behavior, let's see if we can put our stuff into cooked mode. Hold on, I have to do something. I've been a bad boy and haven't been using the thing I built. OK. So the way that we do this, I'm going to get rid of all. We're just going to actually, what's going to happen is we're just going to assume that we're talking to the terminal. Essentially, we're going to stop worrying about whether or not we're writing to. Actually, you know what? I'll do this. I'll put it inside this conditional. So we'll expand this so that if we are talking to the terminal, only then will we be putting it in cooked or raw mode. Because if we try and do that to when we're redirecting to a file or whatever, it's going to go badly. So let's do this. So this is the branch when we're talking to a terminal. I'm just going to duplicate this. Code duplication is great. And we'll say, what did I say? World. We're saying hello to the world if it's not a terminal. OK, so in here, I need to figure out how to put it into raw mode. And there's a way that we do that. So we first have to allocate something, which means I got to go all memscoped. And the thing we have to allocate is called termios. I don't know. You decide. Come on, import. Oh, no. All right, I'll go back to it. All right, and there's a helpful function called cfMakeRaw, which is basically going to take a pointer to this, and then we are going to set our standard out file number. We're going to say apply it right now, TCSA now, with our pointer. That's a pointer, not a para. Why doesn't it like my alloc? All right, I cheated. So I cheated. I skipped ahead a step. we're doing the thing. Remember I said about how curl is reaching around to the T2I device? Well, I had it print that for me automatically. But this is the thing I was trying to do, which is entering raw mode. And what we're essentially doing is creating this structure that has some data. We're setting the right flags automatically to put it in raw mode, and we're setting it against the terminal. And then I have the same stuff down here. So now watch what happens. Does anything look different right off the bat? My cursor's in a weird spot. And that's because when you're in raw mode, new lines just mean go down to a new line. If you want to go back to the beginning, you got to do carriage return, typewriter style. And they don't have to be, you don't have to do like Windows style. So now it's in the right place. And now if I type, you may have thought it was going to duplicate, but it doesn't. And when I press enter, it just goes back to the beginning. What's happening here is the echoing has stopped. When I'm typing hello, that's the application receiving my key presses instantly and rendering them instantly. And so if I do the ABC thing again and I go A, B, watch what happens as soon as I hit C. It immediately exits because it's getting that stuff byte by byte. Another way to sort of illustrate this would be to change how we render. And we'll do like, we'll make a hex string. We'll put each one on its own line. Why are you complaining? Because I didn't give you the... So how about now I type hello. I get the hex. I can do numbers, and then A, B, or I can press enter, backspace. These are all just characters, normal characters. I can do Command C to try and quit. It does nothing, because that, again, is just sent to the program. The program has to handle it. That's why I put the ABC thing in, so that if I do A, B, C, it still can exit without me having to go kill the process. So there's a lot of responsibility here. And actually, the shell that I'm using has my back a little, because when you do this, what you actually should do is, next one. this, where you save the current mode, and then you restore that mode when you're done. And so this is basically just good hygiene. Whatever the person who called you was, save whatever they had, do the cool thing that you're doing, and then put it back how it was when you found it. And so this will just render the same. Now, this is a lot of like low-level stuff, and we've just been writing for the Mac. So Kotlin's multi-platform, right? What happens if I do like Linux? I had Linux as a target. There's my IDE syncing. Is everything going to go wrong? The answer is no. This is all going to work just fine. All these APIs are exactly the same. However, if you do a less fun target, like Windows, huge population running Windows, not everything is there. So you get a little bit of the POSIX stuff, open and close. This won't be there though, so it will end up failing. But then all of the like make raw stuff, Windows is like a whole 45-minute talk in and of itself, and I'm just not gonna cover it because you'll see why. And then the other thing I can do here is like, what if I just do JVM, right? And I got to do a little tweak here, main class, that's main KT. Now I'm building a JVM version, and if you thought it was red before, it's about to get real red. We have nothing we've been doing works on the JVM. That sucks. This is the lowest of like low-level terminal interaction, and so there's an ecosystem of libraries, and so thankfully there are libraries that you can use to do this. The one that I used to use is called Wharton. There's nothing wrong with it. I just don't use it anymore because I did the obvious thing and wrote my own. Wharton is really good for sort of like single output programs that you want to look really nice and pretty, just like this. The one I wrote is Mosaic. Mosaic, also a whole talk in and of itself, although we will touch on it. It is Jetpack Compose running in the terminal and outputting text. But it has multiple layers, and so I've basically written these libraries that abstract all this away for you. So both Kotlin native and JVM, and also Linux, Mac, and our best friend Windows. So we're going to use that real quick to basically do all the stuff that we just did for us. And I'm going to cheat, because cheaters always win. And I'm going to add my dependency here, and I'm going to just sort of hand wave all this away and get the Mosaic version of it. And so the core has basically stayed the same. All we have is the things around it. And so this was us reaching out and grabbing on to the TTY device. And that's a fallible operation. It might not be there. You might not be able to get it. In the cases where you're, like, you ever run something and it's like you can't, in the cases where there's not that enclosing terminal, you're running it outside of the context of where terminal is. And then we basically just get this one-liner for raw mode that's doing it, and it will do the right thing on Windows. Windows is a whole other thing. But then, yeah, it has read and write methods, just like we were using the normal ones. And so if I run this again, we get exactly the same behavior. And I was supposed to show. OK, install JVM dist. And that goes into, we think, build, install. Yeah. Yep. So this is the JVM version. It's yelling at me because I'm on the latest JVM, and we're using native functionality. That's fine. But same thing, now on the JVM. That was ABC. OK. Other than just producing escape sequences that affect the visual representation, there's like a whole secret language that you can talk to the terminal with that it will reply in its secret language, none of which is surfaced visually to the user. There's this exhaustive document. It's really old, but it's also kept up to date. And I want to show you some of the things that we can do with it here. So I'm going to look for something that we're going to do. we're just going to send this CSI, which is our escape sequence, square bracket, and then a number, and then the lowercase letter c. And the only one we can send is 0. And what we're doing is we're requesting attributes from the terminal. It's going to tell us how, at like what level of capability can we talk to the terminal. So there's our CSI 0. I'm going to switch back to native. Oh, I also forgot to say that because we're reading byte by byte, and then we're just echoing it back out, what I'm doing is I'm taking the escape byte, any escape bytes that come in, I'm just changing them to be a period, because otherwise the terminal will interpret that as an escape sequence and try and like act on it. And what I actually want to do is print it. We could have printed it in hex, but I want to like see the actual characters. So this is ghosty. It's telling us that it is replying with 62, and 62 right here is a VT220 capable terminal. If you're a user of the built-in Apple terminal, it replies with this, 1. And 1 is the original VT100, the base most spec. And so why this is important, this is sort of like the first thing you would ever do is to determine like what language your terminal speaks, right? Because if you're speaking in a way, if someone comes up to me and sprechen Sie Deutsch is me, and I say no, and then they just keep talking German to me, like, it's not gonna work. And we can see that in practice. So if I add something else, like this is another thing that I'm gonna query for. 2048 is this mode, and if I run it in Ghosty, it's like, yep, 2048, and 2 means it's off, but it also means you could turn it on. If I run that in the Apple one, I get a P. Oop. And the reason I get a P is because the language of this terminal escape sequences that it speaks stops parsing after the first character after the number. And so this P to it is just like normal text that needs to be output. And so I get pi. But if I were to do that in Ghosty, I only get the IE because it understands that sort of like higher level and then it's before because it answers afterwards. So that's why it's important to sort of have that initial exchange. So another feature of, and there's a ton of these like secret back channel messages you can be sending to investigate what's going on with your terminal. In that mosaic thing, so the mosaic TTY is sort of the lowest layer of abstraction. There's a middle layer of abstraction called a terminal, which I'm going to cheat here and have automatically rewrite for us. It's not that different, so we still have the binding of the TTY, and now we're just doing this. We're doing as terminal, and it's launching a coroutine because it's communicating on our behalf, and we're just consuming the events that it is able to understand. And this will really illustrate sort of like all the different things that you can infer from a terminal. And so this is parsing those into data classes, and then we're just getting the data classes as the toString. So here's the original thing that we tried. The device capabilities, the 62, and these are like attributes on it. Testing for a bunch of other stuff. It can tell that I'm in light mode. It has these other things that we're going to look at in a minute. Here's the version of the terminal. It knows that the terminal is focused. It knows the terminal's size. And so this is live running. So if I do something, like I split my terminal, look what has happened up here. Whoop, things are happening. It has resized. It has detected that the size has split in half. It saw that it lost focus because I'm down here now, and I clicked up here and it got focus. If I toggle my theme, I get theme events saying that, oh, I wonder why my font got so small down here. So there's all kinds of fun stuff that you can listen to. And if I type, I get keyboard events. And not only do I get keyboard events, but if I enable these modes, check out what else I get. If I move my mouse, I get mouse events. I can click, I can drag. That was a nice, ooh, I really like that. Yeah, it's a freaking terminal, and it knows where the mouse is. I mean, think of what you could do based on the mouse position. You can essentially create drag and drop user interfaces in the terminal. It's completely wild. Okay, we are very quickly running out of time. This is sort of like the foundation on which you can build literally everything that's ever been built in the terminal. This is the mechanism by which all of the cool stuff that you've ever seen has happened. And so I don't know if any eagle-eyed people saw, well, typing and talking is not fun. Eagle-eyed people saw this at the very top of my terminal. Watch what happens when I run. Actually, I'm just going to run the whole thing. When I run Gradle, look at the top of my terminal. You see that blue thing going across? That is reflecting the progress of the Gradle build. There's some cool tricks. Oh man, I really wrecked the terminal here. Okay. There's some cool tricks to look at the mechanisms that other applications are using to do things like this. So if I run that same Gradle build, rerun tasks, in this thing called, never had to say this out loud, ASCII-NEMA? Sure. And I'm going to call that Gradle.cast. So it's going to run the program in an enclosing virtual terminal, essentially, and capture everything that the program outputs. Oh, release build. Maybe I should have just done debug build. Okay, there we go. And now if I open this over here, we see things that we should hopefully recognize, right? Like, look at the very first thing on every single line. It is our 1B, square bracket, that's CSI. Then 3A, that's cursor movement. Over here, that is 1M is what, bold, I believe, that we did that early on. And then this one is the cool stuff. So 941, OSC 9. And then look at this fourth number in that. So here it's 17, and then look over here at the progress bar what the percentage was. 17, if I go down here, 64, 64. So this is Gradle telling the terminal that it's 64% through its thing so that the terminal can render a progress bar. If you're on Windows, it's easy to make fun of Windows. The new Windows terminal is really nice. So if you ran a Gradle command in the background and switch tabs, the actual tab itself will show the progress, so you can sort of infer what's going on in other tabs. Okay, I gotta speed run some of these. Check this out. That's an image. That's not text. I can zoom in and I see some pixels. Yeah, you can just yeet whole images into the terminal. You can also do looping stuff. Oh, did we kill it? I was going to say you can do looping stuff, but not in Ghosty. It does not loop. This is why it's important to do that interrogation thing, that interrogation dance, because some terminal, you want to see what it does in here? Let's see what it does in here. Oh, I can't even so there's this other terminal called Kitty, and if I do the same, sorry, it's kitten, that's why. If I do it in here, it actually loops. And that's not like I can still do stuff down here. It just is gonna run and scroll, and it's gonna move with the text. All right, and the very last thing, so that's just start thinking of the things that you could build by combining all of the things. I was talking about the mouse input detection. How about the fact that you can render, you could be rendering images, putting them on screen, detecting when the mouse was over it, got the mouse down, and then be moving the image as it's literally just a full-fledged, it's a terminal for text. It's a full-fledged graphical development platform nowadays. It's absolutely insane the types of things you can build. And so the very last thing I want to show is the thing I kind of wanted this talk to be about, but wasn't ready yet, which is this mosaic thing, which is using Compose to build terminal UI. And so if you've ever seen any Compose UI for Android or Compose UI multi-platform, this should all look exceedingly familiar. You know, we have all the Compose niceties here. We're looping, we're making a count. Except our UI composable here is a mosaic UI. And our output target here is the terminal. Okay. That's what? Samples, count. Oh, I got my suggestions back. That's nice. I meant to build this beforehand. Hopefully it won't take too long. So what this is going to do is, this is why I did stars earlier. Just let the terminal figure it out. Or technically that's the shell that figures it out. Oh, you know why? Look, it's running Linux. I guess I should have put like Mac OS in there somewhere. All right, fine. I'll do it the hard way. Not to like also be evangelizing shells, but my shell is fish, and it has all these really nice things like this, where I can figure out the thing that I want, and it will let me sort of navigate around. All right, so this is like the declarative terminal UI, right? Like nothing, I didn't write anything to tell it to go and put the cursor back and put it in the right position and do all this stuff. I just did the declarative, like this is what I want to render. And there's another one of these. Let's see if I can do it really fast. Demo. Of course it has to build though. Demo. So like here's another one where we're showing, it's supposed to be true color. It's a little, when the terminal's really wide, I guess if I zoom out, it'll get bigger. And you can sort of see the gradient there where it's, you know, the table we looked at, another thing I skipped, the table of colors we looked at had like the 16 or whatever standard colors. You can do full 24-bit true color, which is what this is showing. All the Compose animation stuff, so this is based on Compose animation. And then you can see there's just like another thing with the terminal size also in this. So there's a lot of potential here. And then the very last thing I'll say, though, is despite thinking that, you know, it's all text, like it must have great accessibility, choosing to do a terminal UI is honestly not the greatest choice. And people who are of low vision actually have real problems with a lot of the popular terminal frameworks. Especially the ones that a lot of the LLM things are written in. They just do the dumbest thing possible and repaint the screen every single time. And it's absolutely unusable in contrast to something like Vim, which will work over like a 9600 baud modem, you know, and it will feel like really fast because they're doing like the absolute minimum number of cursor movements and outputs and that just makes it fast. And that also means that screen readers can only speak the diffs that are being put on screen as opposed to having to repeat, you know, the entire thing. So just because it's text, I just wanted to stress on this, just because it's text does not mean it's automatically accessible. So if you're ever building something like this, try and think of, you know, what a low vision or something user would see. So that's everything I got for now. This is sort of like a part 1 talk. I'd love to give sort of like a really deep mosaic talk at some point as well, but this is all the fundamentals. This will translate to the frameworks in Rust, Go, Python, anything that you want. And so all of this foundational stuff you should be able to take, and hopefully you'll now start noticing and understanding. And when you see a program doing this, be like, oh, I understand now like what they're doing behind the hood. And that's all I got. Thanks for listening.